Hello, and welcome back to Aerodynamic Tetris here on Let's Code Physics. As you can tell from the variously shaped pieces that are falling on the screen, I have succeeded in implementing all of the Tetris piece shapes into the game here. Ooh, nice, a vertical one. I could use it over on the left-hand side. So the code is randomly selecting each of these shapes, and then I am rotating them with the up arrow key, moving them left and right with the left and right arrow keys. And so basically we are playing standard Tetris now. It will clear out a row whenever I complete one. So let's try completing one here. I'm leaving myself with not a lot of options for the ending here. And so what I need to do today is add in the lose condition, because right now I can just keep playing and playing. The blocks don't care if they get stuck at the top. I mean, they won't proceed any further. Oh goodness, I need a J piece or an L piece or an O piece. So what I need to add in this video is the lose condition. I'll also show you a little bit about how I've got the shapes set up. Oh yes, finally, as you can see, they're each rotating in the way that you would usually expect them to. Here we're going to clear out 2 rows. Yep, I need to add in sound effects. I'm not entirely sure whether you can do that in VPython, but you know, it would be cool if you could. Let's go over to the piece generation. Let me show you what this looks like. So here, whenever we need to create a new active piece, we pick a random number, and basically we're evaluating it in terms of 7s, because there are 7 possible Tetris pieces. So for this first part, we get a T block. For this next part, we get an I block. For the next part, we get a J block, and so on and so on. And for some reason, I have named both of these J. I see that that's a problem with this. Let's see if we can figure out which one is J and which one is supposed to be L. So if you look at these, we have the active field, or excuse me, the active piece position. So this is where it starts out. So there's almost always a piece that starts in that active position, and then the other blocks are recorded based on the other blocks are recorded relative to that. So let's see here, for example, I've got one that goes below the active, or excuse me, the first piece. Here I've got one that goes to the right, and here I've got one that goes to the right and down. So let's take a look at this here. So I need to start with the active piece position here. So this is going to be kind of the key. Let's draw that coming over here. There we go. Let's even get a different color for the others. So this piece here needs to go to the left of that position. So I've got one piece that goes here. That's going to be this one here. And then I need another piece, let's see, just to the right of that. One to the right of the original. There we go. And then this last one, I'm almost running out of colors here. This last one needs to go to the right and then down one. So that's going to be this last piece over here. And so if I rotate that around, so if you take this piece, rotate up here, take this piece, rotate up here, that's a J, which means this one is actually the L piece. Okay, I'm not sure if that makes a huge difference later on, because they should rotate the same way. Let's take a look at how these things rotate. So the rotation is controlled under this key input function, where the program waits for you to press a key. We've already talked about how we move the pieces, so we'll skip over that part. Here's where we're checking for a rotation. So if you press the up arrow key or the W key, then we're going to check for whether the thing can rotate first. First, we're going to take a look at the vast majority of the pieces. So this is J, T, L, S, or Z. They all follow the same rotation rules, which is you identify the 0th piece in the list. That's the anchor piece. That's the piece that's the block that stays in position. And then everything else just rotates around that. Basically, you calculate the relative position vector between the current block that you're looking at and the 0th block, the anchor block, and then you perform a rotation here that rotates counterclockwise. If it's the I piece, though, it's a little bit different, because the I piece's position is recorded between 2 blocks, so that's why you have all these halves and -1 halves and 1.5 and -1.5 halves down here. So the I piece presents a little bit more of a complicated picture. It takes several lines of code to rotate. But then you come down here and you get to the easiest piece to rotate, which is the O block. which doesn't do anything. You don't rotate it. So I've just got a placeholder here so that we can check that. If we ever needed to do anything with the O block, we can. And then if we were able to rotate, then we just have to update the height and width of the piece. So basically we're swapping the height with the width, and that'll be important in the next episode when we add in our drag force. Okay, so we've talked about checking for the lose condition. So we want to check for whether the newest block can appear. So I think the best way to check that is going to be up here where we generate the next active piece. And what I want to do is check for whether the new piece overlaps existing blocks, or frozen blocks, I guess I should say. Frozen blocks. And the way we're keeping track of the frozen blocks now, is with this list called grid. And so grid is keeping track of all of the squares on the field. So imagine you divide the field up into a grid of squares, and you're basically checking for whether each of those squares is filled or not. So what I want to do is check for whether any of the squares are visible, because if they're visible, then we have the thing blocked. So what I'm going to do is take this, because this is how I'm able to check for these things, copy, and paste it up here as my reference. Okay, so what I need to do is loop over all of the items in active piece. So I want to loop over 4, what have I called these? 4 block in active piece, or excuse me, square. Okay, 4 piece, square in active piece. There we go. And now I want to see if the grid at this grid index, so my, let's see here, so I have to give it a position vector here. So I should just need to give it piece square dot position. So the way this grid index function works, it takes in a position vector and spits out the grid square with all of its properties. So if the grid of the grid index here is visible, then we lose. Perhaps I should say, you lose. Good day, sir. There we go. Let's see, so what do I need to have happen there? I need to set falling equal to false, right? And then I need to maybe print a message or something, put up a label that says, let's just say that right there. You lose, good day, sir. Copy, paste. I'll fiddle with the details of it in a second. I just want to make sure that I've got the logic working correctly here. So actually what I want to do is set falling equal true up here, because that will freeze this. Let's see, so we turn falling to true. We only turn it to false if the square is already visible. If the square isn't already visible, this doesn't get triggered and we just continue on our merry way. Okay, let's try that. Let's hit Control 2 to run. And I'm going to intentionally lose this game of Tetris by just allowing the blocks to fall on top. Uh-oh, we ran into a problem. Oh, I see what the problem is. So it says cannot read property visible of undefined. So because this block starts outside of the grid, it's checking for grid squares up here that do not exist. I believe that's what's happening. So I need to be able to return some kind of error message from here. Okay, I think I found the problem. The problem is that when I was checking for the lose condition, I was telling it falling equals false, and I forgot to have it exit the main loop, because this while falling loop is only one loop. The main loop is while the game is going on. This is while the game is going on. And so what I had to do was create a new variable called lost. And so we start out with lost equal to false, because you have not lost yet. And so I changed this while true to while not lost. And so when we come down here, when we reach the lose condition, we have to set the falling equal to false and lost equal to true. That will get us to exit these loops one last time. I've also put in a check for whether we've lost here when we are turning squares visible. Basically, you don't need to lock the last block in place if you have lost. Now, the only thing I need to check on is why this label is not popping up. Oh, I see why it's not popping up. I didn't say text equals that. Goodness gracious, I'm wondering about that for like half an hour now. Okay, so I've increased the speed so that it can lose faster. I've also added some print statements that I'll need to get rid of. There we go. There we go. And so there we lose, and I can move this around, which tells me that the program is still working. So I'm going to get rid of those print statements off camera, and next time we're going to finally incorporate some physics into this thing. Thank you so much for watching. I will see you next time. Bye-bye.